Welcome to the Deep Dive, where we take complex foundational texts and try to build a shortcut directly to the core knowledge.
And today, we are really jumping in at the deep end. We're tackling Chapter 1, Quantum Behavior, from the Feynman Lectures on Physics, Vol.3.
This is the starting line for quantum mechanics in Feynman's series. He wastes no time, just throws you right into the single most mysterious element of it all.
And he really does. The whole mission of this chapter is to get you to accept a new reality, a reality where particles, like electrons, behave. Well, they behave like nothing you've ever seen in the everyday world.
Right. He says they're like neither classical particles, bullets or billiard balls, nor classical waves like ripples in water.
Exactly. They have aspects of both, and that creates this beautiful paradox. The goal today isn't to ask why nature is this way, but to just look at the evidence and learn the new rules.
And the way we're going to do that is by walking through probably the most famous thought experiment in all of physics, the double-slit experiment. We'll look at it for 3 different cases.
Bullets, waves, and then electron.
Let's start with the classical world, the stuff that makes sense.
The benchmarks.
Okay, so first up, classical bullets. Imagine you have a machine gun spraying bullets randomly at a wall.
And in that wall, there are 2 small openings, 2 slits. Behind the wall, there's a backstop, some kind of detector that can, register where each bullet lands.
The first key point is that the bullets arrive in lumps.
They're discrete. You can count them one by one. You get one hit here, then another hit there. They are definitely particles.
So what happens? If we close one slit and just measure the pattern from the other, we get a simple probability curve. Let's call that PDA1.
Right. And if you close the first slit and open the second, you get another curve, TT22. They're centered on their respective slits. Nothing surprising.
Now the big question, what happens when both holes are open?
Well, with bullets, it's exactly what you'd expect. The total probability, P2A2, is just the sum of the 2 individual ones. P12 equals P22 twined plus P22.
Simple addition. There's no interference, no weirdness. A bullet goes through hole 1 or hole 2, and the patterns just pile on top of each other.
That's it. That is our absolute baseline for classical particle behavior.
Okay, benchmark 1 established. Now for benchmark 2. Classical water waves.
We change the setup. Instead of a gun, we have a wave source. We still have the wall with 2 slits, but now our detector on the other side measures intensity.
And intensity is what exactly? It's not just counting lumps anymore.
No. Intensity is about the energy the wave carries. It's proportional to the square of the wave's amplitude, its height. So where the wave is big, the intensity is high.
So we open both slits for the waves. Does the intensity just add up like the bullet probabilities did?
Absolutely not. Yeah. This is where we see a totally different phenomenon. The resulting intensity, I12, is definitely not just I dollar plus I20.
Because the waves interact with each other.
They interfere. The wave coming through slit 1 and the wave coming through slit 2 travel different distances to get to any given point on the detector.
And sometimes they arrive in sync, and sometimes they're out of sync.
Right. When their in-sync crest meets crest, they add up. That's constructive interference, and you get a bright spot, a peak of high intensity.
But when they're out of sync, crest meets trough, they cancel each other out.
That's destructive interference. You get a spot with 0 intensity, a trough. So what you see on the backstop is this classic striped pattern of bright and dark bands, the interference pattern.
So the dividing line is crystal clear. For particles, probabilities add. For waves, intensities interfere.
That's the classical world in a nutshell.
And now we get to the heart of the matter, the electrons.
Here we go. The setup is the same, but now we have an electron gun. And our detector is a bit more sophisticated. Maybe it gives a little click every time an electron hits it.
And that click is important, isn't it? What does it tell us right away?
It tells us that electrons are arriving in lumps, just like the bullets. We hear one distinct click, then another. They are arriving as discrete whole particles. That's observation number 1.
Okay, so they're particles. So if we close one slit, we should see the same pattern as the bullets, right? It's just a simple probability curve, $.
And we do. Everything looks perfectly classical so far. They're behaving just like little tiny bullets.
But then we open both slits.
And this is the moment that breaks classical physics.
Yeah.
The pattern that forms on the backstop, the total probability P12, is the interference pattern.
Wait, the wave pattern, the stripes?
The exact same stripe pattern we saw with the water waves, with peaks and troughs. And remember, we're firing these electrons one at a time. An electron leaves the gun, a little time passes, we hear a click. Another one leaves, another click.
So a single electron seems to be interfering with what itself?
That's the paradox. The result is clearly not P-1 plus P-3. The classical logic fails.
What's the classical logic that fails? Is it the idea that the electron must go through either hole 1 or hole 2?
That is precisely it. If you assume it must go through one or the other, then the math has to be $p plus p22. But the experiment gives us an interference pattern.
So the conclusion is unavoidable.
It is. Feynman's big insight here is that when both slits are open and you're not looking, the very assumption that the electron went through one specific hole is false. You have to abandon that idea.
Okay, so if our classical way of thinking about probability is broken, we need a new way, a new kind of math for this.
We do. And this is where Feynman introduces the idea of a probability amplitude. It's a complex number, which he labels with the Greek letter phi.
A complex number, so it has both a size and a phase, like a little arrow.
Exactly. And the new rule for the universe is this. The actual probability, to dollars, of any event happening is the square of the absolute value of this probability amplitude. So pi equals the magnitude of phi squared.
And using these amplitudes, we can finally write down the new rules of quantum mechanics.
There are two fundamental rules that come out of this experiment. Rule 1 is for interference. It says if an event can happen in alternative ways that are, and this is the key, indistinguishable.
Meaning we can't possibly know which path the electron took.
Right. If you can't know, then you must first add the probability amplitudes for each path. So the total amplitude, capital Phi, is phi 1 plus phi 2.
And when you square that sum to get the real probability, the math naturally produces those extra cross terms.
The interference term. That's where the wave pattern comes from mathematically.
So what's rule 2?
Rule 2 is for when there's no interference. It says if you perform an experiment that is capable of determining which path was taken.
Like with the bullets, where you could theoretically see which hole each one went through.
Exactly. If the path is distinguishable, then you don't add the amplitudes. You add the final probabilities, just like in the classical world, equals p-1 plus pd2.
So the entire quantum weirdness, the interference, it only shows up when it is fundamentally impossible to know the path.
That's the core distinction between the classical and quantum worlds right there.
Okay, so this naturally leads to the next question. What if we try to know? What if we set up an experiment to watch the electrons and see which slit they go through?
A fantastic and crucial question. Let's say we put a very bright light source right behind the slits. To see an electron, a photon of light has to bounce off it and go into our detector.
So we are forcing the path to be distinguishable. We're trying to force rule 2 to apply.
That's the goal. We turn on the light. We can now tell for each click, that one went through slit 1 or that one went through slit 2.
And what happens to the pattern on the backstop?
It vanishes instantly.
The interference pattern is gone.
Completely gone. The distribution collapses back to the classical bullet-like pattern. P12 is now just p1 prime plus p2 prime. The act of observing destroyed the quantum behavior.
So just looking at it changes the outcome. But why? Is the photon hitting the electron just, knocking it off course too much?
It is a physical disturbance. The measurement is not a passive act. For the photon to tell you where the electron is, it has to interact with it. It has to scatter off it. And that transfers some momentum.
It gives the electron a kick.
A significant kick. Enough to mess up the delicate phase relationship between the two paths that was necessary to create the interference pattern in the first place.
What if we try to be more gentle? Could we use, say, a much dimmer light? Or maybe light with a longer wavelength so the kick is smaller?
Now you're getting to the heart of the trade-off. If you use light with a very long wavelength, the momentum kick is smaller, sure, and you might preserve a little bit of the interference pattern. But with a long wavelength, your vision is blurry. You can't resolve the electron's position accurately enough to say for sure which slit it went through.
So you can either know the path and have no interference, or have interference and not know the path.
You can't have both. It's a fundamental trade-off baked into the laws of nature.
And this whole series of experiments, bullets, waves, watched electrons, it lets us finally state some general principles of quantum mechanics.
The first two are basically our Rule 1 and Rule 2, about adding amplitudes for indistinguishable paths versus adding probabilities for distinguishable ones.
And the third great principle, it comes from that trade-off we just talked about.
It does. The experiment where we watch the electrons is a perfect demonstration of the uncertainty principle, Heisenberg's principle.
We've all heard the name, but how does this experiment show it in action?
It shows that you can't know everything at once. To pin down the electron's position, to know which slit it went through with low uncertainty, a small delta x, you have to hit it with a high-energy photon.
Which gives it a big, unpredictable kick.
Exactly. A large change in its momentum, a big delta P. So the more precisely you determine the position, the less precisely you can know the momentum, and vice versa.
It's not because our instruments are bad, it's a law of physics.
It's a fundamental property of the universe. The uncertainty in position times the uncertainty in momentum can never be smaller than a certain fixed number. It is impossible in principle to know both perfectly.
So the weirdness isn't a bug, it's a feature. The idea that a particle even has a perfectly defined position and momentum at the same time is just not how the world works at that scale.
That's the ultimate lesson of this first chapter. The universe, at its most fundamental level, operates with a kind of built-in fuzziness.
This has been, well, a genuinely deep dive. To just quickly recap, the double-slit experiment shows us that quantum things, like electrons, arrive as particles, as lumps.
But the probability of where they'll land is governed by the math of waves, which gives us interference.
And that bizarre wave-like behavior it collapses back to normal particle behavior the instant we try to find out which path the particle took.
And that brings us to the final thought, the real philosophical challenge that Feynman leaves you with.
Which is?
When you see that interference pattern, when the path is truly indistinguishable, there is no meaningful answer to the question, so which hole did the electron really go through?
You just have to let go of the question itself.
You have to accept that in that situation, the path is not just unknown, it is unknowable in principle. And that's a difficult but necessary adjustment to make.
A fantastic place to leave it. Thank you so much for joining us on this deep dive into quantum behavior. We'll see you next time.